Now, we are going to define a measure that measures the magnitude of the prediction error. So, to study that, we need to, I would like to review the basic idea behind the variance formula. So, when you learn the variance formula, the sample variance was defined in this way. So, variance of a random variable y can be calculated by subtracting the mean from each observation minus its mean, sample mean, and square. So I called it deviation. So deviation is squared, and then the squared deviations are summed, added up, and then divide them by n minus 1. So this was the sample variance formula, and this is the most widely used variance formula when you calculate the variance. And remember, so the formula itself, rather than the formula itself, what I want to tell you here is it is a measure of the average variation in the variable y around with respect to its sample mean. So here is sample mean, then your observations will be spread around the mean. So the center is the mean, and there must be dispersion around it. And how far those observations are from the center, that's what the variance is measuring. So the variance measures basically the distance between the center and your observations. Here, the numerator in that regard, the numerator captures the total variation in y. So y minus y bar, the y observation minus the sample mean, captures the distance, how far, and by taking squares, all the distance, the differences become a positive number. So you may call them distance because they are positive. And so when you sum them, it is the numerator, this summation is the total variation in y measured by the distance between the mean and each observation, right? If you could understand this, and if you just take it, if you divide it by the sample size minus 1, then you get the variance. So variance is some kind of measure of variation, and like basically they're the same concept. By the way, later, maybe in this lecture, I'm going to explain why the denominator has to be n minus 1. There is an important intuition behind it, so let me explain that later. So if you take this, if you can agree with this measure, I'm not saying this measure is the only one or the best one, but if you can accept it measures some kind of variation in y, then we can proceed. So then, using the same idea, in your prediction, you can calculate the variation in your prediction, right? Instead of using the realization of test scores, you can use predicted test scores using from the regression model. From the regression model, you predict y, and using those predictions, you can calculate their variation. But in this case, a special simplifying algebra is that the sample mean of the predictors equals to just the original mean. So the average is the same. And also in the same way, you can define the total variation in the prediction errors, right? Ideas are the same. So U hat is the prediction error, the residual, and calculate in the same way. Just here, this is the sample mean of the residuals. But also it can be simplified because the mean of the residual is always 0. So on average, the prediction error is 0. Otherwise, your prediction is overestimating or underestimating, but the OLS estimator doesn't. So the sample mean of the residual is always 0, so it goes away, it disappears. Anyhow, we can, so from the basic decomposition of the actual realization into your prediction plus prediction error, then for each of them, you can define the total variation in Y and total variation in your prediction and total variation in your residuals. Then you can derive, mathematically you can derive something like this. Total variation can be decomposed into explained variation plus unexplained variation, where explained variation means the variation in your prediction, but unexplained variation is the variation in your residual. So this is the definition. Then our question is, if your model is doing well, then obviously you are going to have very small residuals, and a high percentage of variations can be explained, can be observed into this part, right? So in the extreme, if the residuals are 0, if all the residuals are 0, so that your prediction is perfect, then in this decomposition, the residuals are 0, so the unexplained variation will be 0. So 100% of total variation is explained variation. So this is how we define the R square. Total sum of squares. So by the way, I defined total variation and total variation in prediction, total variation in residual, but they are called, they have names. The total sum of squares, it's intuitive, total sum of squares, so sum of squares for the total value, total y, and sum of squared errors, explain sum of squares. Explain sum of squares is total variation in your predictions. So this is called ESS, explained sum of squares, and the residual sum of squares is intuitive. This is variation in residual, which is considered as the unexplained variation in Y. So TSS, ESS, RSS are the typical names for them, but annoyingly there are maybe equally commonly used names, different names. So in some say sum of squared, total sum of squares are denoted as SST, and sometimes explained sum of squared is referred to as regression sum of squares, and residual sum of squared is referred to as sum of squared errors. Then the problem here is sum of squared error is denoted as SSE, and regression sum of squared is denoted as SSR. So those two, the anonyms are switched in different textbooks. So I don't like these terms, so I'm going to just use my own term. Variation in Y and variation in prediction and variation in residuals. This is good enough, I think. So the name, if you open up different textbooks, you may find a different term. So don't be surprised doing the same thing. Anyhow, back to the definition. In the definition, in the denominator is the total variation in Y, total variation in the test score, and numerator is the variation in your predictions. So as I said, if this equals to 1, then there is no residuals. And if this is 0, then everything is residual. So it is always between 0 and 1, and of course the better the model is, the more close to 1 the R squared is. So as the R squared increases, that means you are explaining more about the test score. That is the definition, right? It's intuitive, so you can say how much percentage of variation is explained by the model. And I'm going to explain this sentence here. And you may understand the R squared in a different way. That is, suppose, so we have Y, which is the actual realization of test score, and you predict Y as Y hat. It is another number. You may compare these two. And another way to compare them is to calculate their correlation coefficient, right? So if your prediction is good, then Y hat will be very similar to Y. So Y hat will be very much correlated with Y. So the correlation coefficient will increase to 1 if your model is good, if your prediction is better. So in this case, R is the correlation coefficient. If the correlation coefficient is 1, that means prediction is perfect. If 0, that means it's of no use. It's just a random guess. You are randomly guessing the test score, so there is no value at all. And even more extreme case is when the correlation coefficient is negative. That means the predictor is worse than a random guess. So you don't need to do anything. Just don't look at the data and just guess at random. That would do better. So we don't consider this strange case. So as a result, again, correlation coefficient lies between 0 and 1 if you ignore these stupid cases. And then mathematically, what you can show is that the R squared we defined as the ratio between explained sum of squares and total sum of squared can be written as the correlation between your prediction and the actual values squared. So actually the correlation coefficient approach is the original. This is the original approach, so it's named as R squared. But later it's found that this kind of interpretation could be better. It's your choice, but it's very widely used and very intuitive and very clear what we are doing, and also it is unit free because it's always in between 0 and 1. So without knowing the units of the variables, you can tell how good you are doing. So these are very nice measure. Okay, I'm going to continue the next measure in the next video.